you ever thought about things in life that you think you might want to do one day, but you always think, oh, I'll get to it someday? Well, you only live once, my friends. Gotta make sure one time is enough. I've always thought about measuring my neighbor's palm tree. I always wanted to be the life of the party. Talk is cheap. The day has come to actually do it. Got the key right here. Okay. I'm gonna tie this up right here. Tie a little clip onto it. I don't even tie it, I'll just snap it on there. And I'll roll this baby. Roll it. Roll it, roll it, roll it, roll it. Like a burrito. What do you guys think? Got this. That's all we need. Talk is cheap. Let's do it.
Papi?
Yes, mijita?
I have better.
Good. You know what we're doing today, mijita?
No.
Today we're gonna do Carpe Diem.
Okay.
You know what Carpe Diem means?
No.
Carpe Diem means seize the day. You know why I say that?
No.
Because I always talk about something and I never do it. I always talk about if there was a tree here.
I know trees.
You know trees? I always talk about, could you just look at it and measure it?
Papi, I know
If
that
you could,
I know
you would
that,
be
I know
the life of the party.
Papi,
Yes?
I know that sound. Tree.
You know that sound?
Yeah,
Tree?
the tree.
Oh, the tree. Yes, you know that word, tree. Hey, you want to go measure it? You want to be my helper? You and Diego? I think it's time we seize the moments.
Okay.
Talk is cheap. Let's actually measure it. By now we have all the tools, mija.
How?
How? We have this excellent life of the party tool. And we've got the key. We've got the whole wide world. And we've got this. With this, we're going to measure the tree.
That makes measure things.
That makes measure things to fix. Yes, you're right. You ready? Let's do it.
Papi,
Carpe diem.
I thought
Can you say? Can you say carpe diem?
Papi,
Carpe diem.
Papi,
Monday.
I thought that thing to fix stuff in the Manny show.
Oh, in the Manny show, of course. Let's do it.
Helpers of Fabi.
You ready, Diego? Okay, you see that tree right there, mija?
Yeah.
We are going to measure it. You ready?
Yeah.
Ready, Diego?
Yeah.
We're gonna look at the very, very top of the tree,
Stop, Bella.
and we're gonna measure the angle.
Yeah.
You see this little hole right here? You see the hole in there? I want you to stand right here
Where?
on the tape, yeah, and look at the tree now. Turn around. Look at the tree. Okay, now I want you to look at the hole and point at the top of the tree. Yeah, that tree. No, no, no. Not point it with your finger. Point it with the paper. Look inside the paper. Can you see the top of the tree? Can you see the top of the tree?
Yeah.
Through the little hole in there.
Yeah.
Yeah. It's very, very, very top of the tree. Now let this go. Let it go. Can you look at it?
Yeah.
Okay, let me show you how. Okay, you're about to get fired from this job.
Nah.
Okay, you're doing a good job now. You looking at the top of the tree?
Yeah.
Very, very top of the tree. Now walk back. Walk back. 10 feet. 10. Find the number that says 10. Right there. That's it. That one right there. Now do that again. Do what you did for me. Do it again. Now look at the top of the tree.
I don't want to go so that makes my eye hurt.
Okay. Just look at the top of the tree as best as you can. You looking at the very, very top of the tree?
Looking at the middle.
Well, don't look at the middle. Look at the very, very top of the tree.
Still.
Any day now. Now you are? Now you are?
Yeah.
Perfect. See? We're looking right there at the top. The very, very, very top of the tree. And then we're going to see what degrees is that. Okay? Okay guys, good job. Give 5. Good job, Diego. Say you know? Did you get 5 from this job? Just about. Hey, that was fun. So let's recap here. First, we looked at the tree from the bottom of the trunk. We got lower enough to where the angle was exactly 0. Then we looked at the tree and it was 31. Let's just say 31. And then we stood back 10 feet and then it was
That's right.
24 degrees. That alone.
Right.
Okay, that should be enough for us to figure out exactly how big the palm tree is, as I promised. Talk is cheap. It's time to get the job done.
Get the job done. That's right.
Okay, Mika, that's enough.
So much.
Okay, so then we stood back, and this was exactly 10 feet. 10 feet, and then we looked up again. And we looked up again, and then it was, I think I remember it was 24 degrees. And that's it. From those two measurements alone, you just look at it, boom, and then you stand back a few feet, look at it again, and that's enough. That's enough for you to be able to figure out how tall the tree is. Well, hopefully by the end of today. Before we get to that, okay, so before we get to that, by the way, just let me point out that, you know, with the help I had, it was a little bit difficult to measure this angle. It might have been 31 or 32. The actual number is really immaterial, so we'll just go with 31. That being said, here's the way we're going to attack this problem, okay? Again, one of the main ideas that trigonometry is concerned with is that of solving triangles. So what we're going to do is we're going to leave this. See, if you cover this, that's a triangle right there, but that's not a right triangle necessarily. So this is a slightly more problem than if you cover this and you solve this triangle. This is a right triangle. This is in many ways a much easier problem to tackle. So here's the game plan for today. For today, we're gonna put this on pause for a second, and we're gonna say this is kind of like our dessert. So when we get done with the standard problems, we'll come back and do this one. So we're gonna put it away and just focus on this type of problems, solving right triangles. This will be really good for our psychic. We'll become really good at solving these, and then at the end, hopefully, we will put this one up here, and it will be a piece of cake. All right, how does that sound? So first, let's tackle right triangles. So for example, Suppose I've got a standard right triangle, and suppose I know that this is 10 degrees, okay? And suppose that I know that this is 7 feet, 7 units. That's it. Remember, the big premise for all this was ratios is all you need. If you've got the ratios in one side alone, you've got the rest of the story. So by the way, let's just finish this example. So if you stand from this point of view, the opposite would be over here. Opposite. And the hypotenuse is always across from 90 degrees. So this is the hypotenuse. And you try to think to yourself, which function describes the ratio of opposite to hypotenuse? And of course, we've practiced this entire chapter, the introduction of the trig functions. You know that sine does. So if you were to find the sine here, this would tell you exactly what ratio it is to go from the hypotenuse to the small one. Let's do it here on the side. Sine of 10 degrees would be the ratio of opposite. You guys like the clicking sound? Opposite to hypotenuse. So that ratio is, let me see, I'm going to use a calculator. So I'll go sine of 10 degrees, make sure I'm in degree mode. So it's approximately 0.17. Approximately. That's opposite over hypotenuse. That means that the opposite is about 17% of the hypotenuse. So to go this way, you would multiply by the 17%. Got it? So I'll take that 17, it's still in my calculator, so I'll just go times 7, and that's equal to approximately 1.21, maybe 2 if I round off. See how easy that was? Then you say to yourself, all right, from here, from this point of view, this is the adjacent side. This is the adjacent, and I would like to know a function that tells me the ratios. It's all about the ratios. If you know the ratios, one side is enough. I'm going to say that like a million times. If you know the ratios, one side is enough. If you know the ratios, one side is enough. If you know the ratios, one side is enough. And to know the ratios they're given by the trig function. So we have a tailor-made trig function that describes this ratio adjacent to hypotenuse, and of course that's cosine. So I'll do it off here off on the side here. Cosine of 10 degrees is equal to adjacent by definition over hypotenuse. So I'll calculate it again. I use some standard calculator. Cosine 10 degrees is approximately 0.98. Okay. Any old chump can plug numbers in here, but it takes a human being to be able to understand exactly what that means. Here's the way we understand it. It means that the adjacent one is approximately 98% of the hypotenuse. So to go this way, you would just multiply by the 98%. Get it? So that number's still on there, so 98%, I'll just go times 7, and that's equal to approximately 6.89. And there you go. Now you see why they pay me? Insane amounts of money. From one side alone, we figure out the rest of the story. Oh, by the way, this angle over here is easy to figure out because they have to add up to 180. This one right here is 90 degrees, and these two, if this is 90, these two have to add up to 90. They're called complementary. So the complementary angle to 10, that's whatever is missing from 90, that would be 80 degrees. This would be 80. I'll emphasize it. This is 80 degrees because it has to be complementary to 10. They add up to 90. And there you go. All 6 items of the triangle are completely solved. I told you, solving a triangle, generally speaking, means they give you 3 of the items, you find the other 3. The nicest thing is that if you know the ratios, all you need is one side. If you know the ratios, all you need is one side. If you know the ratios, all you need is one side. All right, so let's do that again here. That was so fun. We're going to do it again. So this time, suppose you have, this one is, I don't know, 12 degrees. And suppose you know one side. Suppose this side is, 12 degrees is too close to 10. Let's make it 25 degrees. Okay, suppose this side right here is 10. That's it. You got 3 items. Look, count them. 1, 2, 3. 3 items. I told you. You got to find the other 3. Oh, I could find this one easy because these two have to add up to 90. So this would be about 60, maybe 65 degrees. There you go, one of them down. Now again, to figure this one out, all I need is the function. I would like the function that describes this ratio here. From this point of view, this is the 25-degree angle. I need opposite and hypotenuse. Well, that would be sine. So I'll calculate the sine here. I'll do sine of 25. That's so to go this way, you would multiply by about 42%. While I'm at it, I'm going to do this one. I'm going to go cosine of 25. So to go this way, you would multiply by 0.91%. Well, now it's all over. So easy. Look at this. Now that I've got the ratios, I told you, didn't I tell you? When you've got the ratios, one side is enough. When you've got the ratios, one side is enough. I've got the ratios because they're given by this sine function here and the cosine function here. Now all I got to do is multiply by 10. So to go this way, you take your hypotenuse and you multiply by that. So I'll take my 10 times the answer, and that was, of course, that's about close to 9.1. Shoot, I don't even need a calculator. I bet you I could do this one without a calculator. Watch this. 0.42 times 10, that's 4.2 approximately. I told you. That's why they pay me insane amounts of money. Okay. Is that easy or hard? I make it look easy, huh? That's why they pay me. Alright, let's try it again. Enough talk. Talk is cheap. Suppose this one was, I don't know, 15. And suppose this time, this angle is 72 degrees. Easy. I got three items, look. I've got the angle, and one of the sides. Now, as long as I have the ratios, I'm in good shape. So I'm going to find this ratio. From this point of view, this ratio is opposite and hypotenuse. The sine function describes such ratio. So I'll just do a sine of 72. It's approximately 95%. So to go that way, all you do is multiply by 95%. This is times. Of course, if you wanted to go backwards, you would divide by 95%. You understand? So to go that way, you multiply. To go that way, you divide. And we'll do one like that next example. Anyways, while I'm at it, I might as well multiply by 15. That gives me my 14.3 approximately. Okay, now to go this way, I need a ratio that compares hypotenuse to adjacent. Adjacent to hypotenuse. Of course, the function that's tailor-made for such ratio is cosine. Cosine describes the ratio of adjacent to hypotenuse. So I'll do a little cosine of 72, and the ratio here is 30%. I'm round off to about 31%. So to go this way, you would multiply about 31% times 15, and that would give you approximately 4.6. 4.6. That's it. That's all you got to do. If you know the ratios, one side is enough. From one side, you can figure out the other two sides. If you know the ratios, one side is enough. And you do know the ratios because you got this cheap, prideless way of finding all the ratios because you got the sine functions here. Okay? Okay, now let's just take it up a notch or two here. Switch it up a little bit. What if you didn't know the hypotenuse? What if you knew some other ones? Because all of this time I've been telling you one side is enough if you know the ratios. So what if I give you a different one side? This time I gave you the opposite. So from this point of view, this side over here is the opposite. This one's the hypotenuse. Hold on, man. Today's gardener day. Let me close the window. Okay, where was I? So one side is given, but the different side is given. So I'll do the same thing. I'll figure out, first of all, which function describes this ratio. The ratio of opposite to hypotenuse. Of course, sine does. We've only been doing that like 20 times already. So I'm going to do the sine of 35. So sine of 30. Sine of 35. So that's about 57%. So to go that way, you multiply by 57%. And while I'm at it, I'm going to find the cosine. Cosine of 35.0, that's about 0.82. This is no different than what we did earlier. The ratio of opposite to hypotenuse is still that would tell you, if you knew the hypotenuse, you would multiply it by 57% to get to that. If you knew the hypotenuse, you would multiply it by 82% to get to that. So now my question is, but you don't know the hypotenuse, you only know the opposite. So first of all, could you go backwards from the opposite to the hypotenuse? How? Well, to go this way, you multiply by 57%. To go backwards, what you do is divide. So I'm going to take my 5 units here and divide it by 0.57, and that would give you, of course, 8.77 to approximately. Now, to go from the hypotenuse to the adjacent, we've got the cosine ratio, which is about 82%. So you would take that number times 0.82, and you get approximately 7.19. I told you. See how easy it is? By the way, when I was your age, nobody ever made it this easy and this clear. Okay? No Math Hands, no Walmart with this, nothing. So nowadays, this is incredibly easy to understand, incredibly easy to carry out. Everything is just there for you for the taking. Okay? Life is there for you for the taking. Want to try another one? Let's try another one. I'm not afraid. Let's switch it up a little bit for fun. What if this time we're given this side? Oh, let's put some angles. Suppose this is I don't know. Let's say it's 42 degrees. Suppose for fun this time I'll give you this side is 10. That's it. 3 items are given: angle, angle, and side. And you know what's good is when you got one side, all you need to know is the ratios. When you got the ratios, one side is all that's needed. I don't know if I told you. I don't know if I mentioned that or not. I might have forgotten to mention it. One side is enough. When you've got the ratios, one side is enough. Watch this. This time I'm going to switch it up a little. All the time I've been doing this this angle right here, which is this ratio, which is a cosine, and that. Watch this. All this time I've been doing this ratio, which is a cosine. I'm going to make that disappear. Come on, go. I told you. That's why they pay me. This side, which is the sine ratio, this is the sine ratio. Well, the sine of this angle right here, because from this point of view, it's opposite. But now, just for fun, I thought, you know what? I've never done this ratio, so let's do it. This ratio, which function is from this point of view? Okay, which sides are these? This is the adjacent, and this is the opposite. Which function is tailor-made to describe the ratio of opposite to adjacent? Of course, tangent is. So tangent of 42 degrees is equal to. Tangent of 42 degrees is equal to. I got my tangent calculator here. Tangent machine. What you got? Oh, this is about 90%. So this is 90% to 0.90 approximately. So 0.90 is the ratio of opposite to adjacent. So that means that the opposite is a small one. The opposite is 90% of the adjacent. So to go this way, you would multiply by 90%. Of course, to go this way, you still do sine. So I'm going to do my sine here. Sine, 42 degrees, 0.67 approximately. And that's it. When you've got the ratios, all you need is one side only. Okay? They say that excellent teachers sometimes just stand there and wait. That's what they say. All right. So, let me see. The adjacent was telling me this ratio is 90%. So to go that way, I multiply. By the way, you got to be careful which way you put the arrow, because if you put it the wrong way, you're doing the wrong ratio. Opposite to hypotenuse is 90%. That's telling you that the opposite is the one that's bigger. or it's telling you, in other words, here's another way you could figure out. You take if I multiply both sides by adjacent times the 90% is equal to the opposite. That's how I know that I take the adjacent and I multiply it by 90% and I get the opposite. That's how I know which way to make the arrow. To go that way is to multiply. Okay, where was I? I'm going to try to do this one in my head. 90% of 10 with no calculators. Watch this. No commercial breaks. 9. Oh, take that. Then you're going to do 90 or 9. Okay, to go this way you would multiply by 67%. If you knew the hypotenuse, you would multiply by 67% to get the opposite. I need to go backwards. So to go backwards, I need to divide by the 67%, not multiply. I'm going to make that disappear. Nice. Alright, so I'm going to take the 9, divide that by 0.67. What does that give you? Approximately, whoa. Oh, we don't want that one to disappear. Approximately 13.43. I divided. Now you see, I told you. What did I tell you? If you know one side alone, from one side, and you know the ratios, game over. You've won. So maybe I could summarize it this way. I could summarize, this is an incredibly important lesson. This is a cornerstone of trigonometry. The fact that if 3 other items are given in the right way, you can figure out the other 3. But by the way, there are cases where you can't. There's nothing that you could do. For example, let's get a little crazy here. What if I told you, hey, this angle is 20 degrees. This one, of course, is 70. Now, how many items have I given you? 1, 2, 3 items are given. How many are missing? 3. 1, 2, 3. The 3 sides. Okay, figure them out. Good luck with that. Let me know how it goes. Because all this time I've been telling you, if you got one side, if you know the ratios, you can find the others. But here you don't know any of the sides. So, sure, you could find the ratios. To find this ratio here, you would just calculate sine of 20 degrees. To find this ratio here, you would calculate cosine of 20 degrees. To find this ratio over here, you could calculate tangent of 20 degrees. But so what? You can't go from any one side to the other because none of them are known. So this is this would be a case where there are infinite many possibilities. In fact, the triangle could be little like this, or it could be big, or it could be big. It could be drawn to any scale possible. All you know is that the proportions. This is 20 degrees, 70 degrees. You can figure out the ratios, but that's about it. This is one of those cases where there are infinite many real solutions to the triangle. In other words, if somebody says, hey, I've got a triangle in my pocket, I won't tell you what it is, but I'll give you some hints about it. One of the angles is 90 degrees, the other angle is 20 degrees, the other angle is 70 degrees. Can you figure out what the angle is? The conclusion should be yes, I can figure out. Your triangle could be any of infinite many of them. All I know is the ratios. So there are infinite many possibilities for the triangle in your pocket. That's what we call infinite many solutions to the triangle. By the way, there are cases where there are no solutions. None. Zero. Nada. I'll give you a classic example of that. Suppose that suppose I tell you, well, that's not the kind of triangle we're used to. Come on, we're going to raise the price on Math Hands. Gotta give you at least something good. Alright, so suppose I give you this. This is 40 degrees and this is 200 degrees. And you say, what? Say what? This is not real. The angles inside don't even add up to 180. They're way, 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 way more than 180. So it could happen, but not in the real Euclidean space. Euclidean means flatland. In flatland, all these triangles we assume are in flatland. You can't have a triangle with more than 180 degrees. It's where in the interior angles. So the point is that sometimes there's no real solution. Sometimes there are infinite many solutions. And on a good day, there's exactly one solution, where at least one of the sides are known and the ratios are known. Game over. Did I say that? Did I mention that? When the ratios are known, one angle. Too much coffee. Let me think. I'm not sure if I mentioned this, but when you know the ratios, one side is enough. Game over. Okay. Okay. So let me summarize. Maybe it's good to summarize this. Let's clear this page. Cleared. Maybe you could summarize it this way. With a big one. Let's go big. More for your money. If this angle is theta here, this is from this angle, from this perspective here, the opposite one is over here. Opposite. The adjacent one is here. The hypotenuse is here. This ratio right here is given by sine of theta, whatever theta you got there. This ratio right here is given by, oh yeah, you have to multiply by cosine theta. This is the ratio of adjacent to hypotenuse. And this ratio over here is given by multiplying by tangent theta, opposite to adjacent. This right here probably would summarize everything that we've done so far in this class. In the last 2 chapters, everything is summarized right here in this picture, like nowhere else before. This tells you so many things. It tells you, well, picture's worth 1,000 words. Just look at it. It's beautiful. Maybe I could do... You guys know what we got to do today? That's what we got to do today. Are you guys ready? We've practiced a lot on right triangles. Are you ready though? I don't know. I don't know if you guys don't look like you're ready. Let me take one more example and then we'll tackle that one. Let's just stare at this beautiful picture for a little bit longer. It's so crucial. So beautiful. To go that way you multiply. To go that way you divide. To go this way you multiply. To go this way you divide. To go that way you multiply. To go this way you divide. Oh no, I messed it up. Let me erase it. Shh, God. I told you. That's why they pay me. Okay, let me do one more example. Enough playing around. Clear this. Let me give you an example where we take a look at a different perspective. Yeah, because these things, they don't always come like this. Let's switch it up. You guys want to do an upside down one? How good are you? And you can't cheat here. You can't turn your TV upside, or your screen upside down. Haha. So suppose I tell you this is 12 degrees. And I give you one of the sides. Suppose this side is 8. That's it. 3 items. 90 degrees. One of the angles, one of the sides. When you got one of the sides, all you need is what? The ratios. The ratios is all you need when you got one of the sides. The ratios will tell you everything. So let me think. From this point of view, this is my angle right here. From this point of view, this is the opposite now, right? From this point of view right here, this is the adjacent one, because it's right next to it. And from this point of view, this is the hypotenuse. Hypotenuse is always across from 90. Oh, that one doesn't erase. Okay. So you think to yourself, which ratio tells me which function will give me the ratio of hypotenuse to opposite? Well, that would be the sine function. So here I got to do the sine of 12. I'll do it right now. Talk is cheap. Sine of 12. That's about 21 degrees. So multiply by 20. So not 21 degrees. 21%. By the way, if you guys haven't noticed, sometimes I say things and I write something else. Just let that slide, alright? I try to be as accurate as possible, but I am so human, I can't even tell you. By the way, I love being human. It's one of the rare privileges of my life. I wouldn't trade it for any other species. Alright, that's how I got the 21%. Now I need the ratio of hypotenuse to adjacent. Of course, cosine tells you that. So that would be 97%. No, I'm going to run off to 98%. And that's it. Now it's all over. Once I've got the ratios, one side is enough. From one side I can figure out the rest of the story. I'll take my 98% times 8. I reckon that's 7.83, rounded off approximately. Let me see, I'll take my 8 times 0.21. I reckon that's 1.68 approximately. That's why they pay me. Upside down, right, left, doesn't matter. Opposite is opposite. Adjacent is adjacent. The triangle could be shaped any which way, as long as a right triangle in flatland, in Euclidean land. Okay, you guys know why I keep putting this one off? Because I'm not sure if I could pull it off. Let's just do another example of the easy ones better. I'm just kidding. The time is right. The moment is now. Seize the moment. We are food for worms. Make your life extraordinary. I love that movie. You guys know where the movie comes from? Where all that stuff comes from? Dead Poet Society, one of the greatest movies ever made by humans. Carpe diem. All right, talk is cheap. Let's do it. You guys ready? All right. Okay, so talk is cheap. Let's do it. First thing we will do is let's look at this. We take this triangle and look at it as two separate ones. On the one hand, we have the first triangle, which goes kind of like this. And on that triangle, that's the innermost one. This is 31 degrees. This side, we don't know what it is. We'll just call it A. So we'll call this one A. This side over here, we don't know what it is. That's the one we're trying to figure out. We'll just call it B. So that's the first triangle. Now, on this triangle, the ratios say, well, let me look at the other triangle first. The other triangle would go from here all the way to, from here to here, from here to here, and from there to there. And this is still B. This is no longer A though. This is A plus 10. This is A plus 10 more feet. Those are the 10 extra feet that we went back, and now this is 24 degrees. Still a right triangle. So what we have here is two triangles, same variables, A and B, A and B. From these two, we should be able to get two equations with two unknowns. So on the one hand, well, we could do this many different ways, but here's one way to do it. This ratio right here is given by tangent. To get from here to there, you get tangent of 31 degrees. In other words, you take A and you multiply by tangent of 31 degrees, and that's how you get B. On the other hand, from this side, the ratio would be tangent of 24 degrees, so you would take this whole thing, okay? You would take A plus 10, and you multiply by tangent of 41 degrees, and that would give you the same B that we have here. B. These are both the same B as the height of the tree. And this, my friends, this is what we call a system of equations. Two equations, two unknowns. You may recall back from algebra where you did problems like that. X times 3 plus 2 is equal to y. 4x plus y is equal to 7. These are famous. They're called systems of equations. Two equations, two unknowns. And you have a bunch of famous tools to solve these, such as Gaussian elimination, Cramer's rule, substitution, elimination, yada 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 yada. Alright, enough of that. Now we've got our work cut out for us. Two equations, two unknowns. We're going to try substitution. So we take this B and substitute it over here. And that would give us A times tangent of 31 degrees is equal to A plus 10 times tangent of 21 degrees. By the way, I don't know why I wrote 41 there. No one stopped me. I should have said something. 21 degrees. No, 24. What the hell? 24 is what I meant there, right? Tangent. This whole thing times tangent of 24 degrees. That's these 24. And now we've got ourselves a nice system of equations. We've done substitution. We take this, substitute it here. Now look what we've got. One equation with one unknown. The unknown variable is A. At that point, we'll solve for A, and then once we get A, we multiply by tangent of 31, and then we'll know what B is. You get it? You get the game plan? So let me see, I'm going to clean this up. A times tangent of 31 degrees is equal to, I'm going to distribute this. So if I distribute that, I get A times tangent of 24 degrees plus 10 times tangent of 24 degrees. Okay? And I'm running out of room. So I move all the A's to one side. Should we start off on a new paper? Yeah, I'm trying to remember those. If not, I'll come back to it. I had, shoot, I forgot. Let me come back to it. I'm just kidding. A31 minus, I'm going to do A31 degrees minus A of 24 degrees. So we have that A times tangent of 31 degrees minus A times tangent of 24 degrees is equal to, I believe, 10 times tangent of 24 degrees. 10 times tangent of 24 degrees. So here it looks like someone distributed an A, so maybe we can undistribute the A, so that would give you tangent of 31 degrees minus tangent of 24 degrees, and that's equal to 10 times tangent of 24 degrees. By the way, at this point I could just compute each one of these and get a decimal approximation. Of course, the more of these approximations that you do, the less accuracy your final answer will have. So I'm just waiting until the very, very end to have less error, less approximations. Tangent of 31 minus tangent of 24 degrees. This is exactly what A is, and now I will approximate. I will approximate using my excellent calculator. So I'm going to go like this. I'm going to go 10 times tangent of 24 degrees, close the parentheses. And I'm going to divide that by, I'm going to open up a parentheses. Tangent 31 plus, negative, minus tangent of 24, voila, times 1.0. is equal to approximately, okay, so that helps us get A. It's approximately 28.61. So we go back to our drawing. This is 28.61. That would be this point right here. Approximately 28.61. Okay. Now it's all over, because now you've got a triangle. Let me see if I can copy just this triangle. Copy. Let's see if we can put it on another page. Let's go to this one. Let's clear this one. Paste it. Good enough. Okay, so now this was 31 degrees, and this was the B that we're looking for. This was the tree. On a right triangle, let me zoom you in there. All you need is one side. When you've got one side, it's all over. Let me approximate tangent of 31 degrees. Tangent of 31.0. This is approximately 60%. So I'm going to take my 60% times my 28.61. That gives me B is approximately 17.19. That's it. I told you. Talk is cheap. Carpe diem. About 17.19 feet. That's how big my neighbor's palm tree is. Okay?
lines of the poem you find there.
So the Virgin's to make much of time?
Yes, that's the one. Somewhat appropriate, isn't it?
Gather ye rosebuds while ye may, old time is still a-flying. And this same flower that smiles today, tomorrow will be dying.
Thank you, Mr. Pitts. Gather ye rosebuds while ye may. The Latin term for that sentiment is carpe diem. Now, who knows what that means?
Carpe diem. That's seize the day.
Very good, Mr.
Meeks.
Meeks. Another unusual name. Seize the day. Gather ye rosebuds while ye may. Why does the writer use these lines?
Because he's in a hurry.
No. Ding. Thanks for playing anyway. Because we are food for worms, lads. Because believe it or not, each and every one of us in this room is one day going to stop breathing, turn cold, and die.